Section: Introduction. In this section, we will discuss the significance of multi-layer perceptrons, MLPs, in today's AI landscape. MLPs are crucial in machine learning, ML, and artificial intelligence, I, alongside transformer architecture and convolutional neural networks. MLPs are commonly used in natural language processing and computer vision. They serve as the primary neural network structure for various ML applications, such as representing the solution operator of partial differential equations and the density or color function in neural radiance fields, NeRFs. They also replace traditional ray tracing with neural ray tracing. Unlike other architectures, MLPs are known for their fully connected layers, where each neuron in a layer is connected to every neuron in the previous and next layers. A key feature of MLPs is that each neuron's output is independent of its neighboring neurons in the same layer, making them suitable for fully fusing operations. Our focus is on efficiently implementing narrow MLPs on Intel GPUs. These narrow MLPs have an arbitrary number of layers, depth, and a small, constant number of neurons per layer, width. Narrow MLPs are of interest because they are universal approximators, have various use cases, and their theoretical peak performance is limited by the small width of the layers. The reduced arithmetic intensity due to the small width affects the matrix multiplications in each layer during training and inference. To address the challenges posed by low arithmetic intensity and memory bandwidth, a common strategy is to fuse the layers into a single kernel to keep relevant data in faster memories like the register file or shared memory. This approach, known as fully fused MLPs, has been implemented for NVIDIA GPUs using CUDA. Here, we focus on a SYCL implementation for Intel GPUs of fully fused MLPs with arbitrary depth and a fixed layer width of 2 to the power of I neurons in each layer, where I ranges from 4 to 7. Our implementation is based on Intel's joint_matrix SYCL extension to utilize the XMX hardware in Intel's data center GPU Max 1550. This method optimizes training and inference performance for models requiring high data throughput with specific batch sizes. Our SYCL implementation on Intel hardware outperforms an equivalent CUDA implementation for MLPs with a width of 64. In summary, our work demonstrates the efficiency of fully fused MLPs on Intel GPUs and their performance improvements in various applications such as image compression, neural radiance fields, NeRFs, and physics-informed machine learning. Our implementation surpasses the off-the-shelf Intel extension for PyTorch, IPEX, and the CUDA PyTorch version on NVIDIA's H100 GPU in terms of performance. Section Summary. In this section, we introduce multi-layer perceptrons, MLPs, and their significance in machine learning and artificial intelligence alongside transformer architectures and convolutional neural networks. MLPs are widely used for various applications like solving partial differential equations, neural radiance fields, NeRFs, and neural ray tracing due to their fully connected layers and independent neuron outputs within each layer. Our focus is on efficiently implementing narrow MLPs on Intel GPUs, which have a limited theoretical peak performance due to their small layer width, leading to challenges in memory bandwidth and arithmetic intensity. By employing a fully fused approach, we aim to optimize training and inference performance, showcasing improved results over CUDA implementations and demonstrating superior performance in applications such as image compression, NeRFs, and physics-informed machine learning. Section: Recognition. In this section, we apply multi-layer perceptrons, MLPs, in various fields such as image classification, object detection, semantic segmentation, video analysis, image processing, and generation in vision tasks. In natural language processing, NLP, MLPs are used for sentiment analysis, opinion classification, malware detection, and multilingual translation tasks. MLPs are also utilized for solving partial differential equations through physics-informed neural networks, PINNs, and neural differential operators. They are integrated into neural graphics for tasks like neural rendering, 3D reconstruction, super resolution, and depth estimation. Our interest lies in exploring the potential of MLPs in these areas, and we will present our findings in the appendix. In the realm of compression, MLPs are employed to reduce data or model sizes by eliminating redundant parameters and operations. They achieve data compression by learning compact data representations that can be accurately reconstructed. Additionally, MLPs aid in model compression by approximating complex models with simpler ones. In robotics, MLPs are crucial for tasks like navigation, autonomous driving, and manipulation. They are also used in structured control networks, recommender systems, pure feedback systems, and gaming for system design and control using deep learning techniques. MLPs are widely used in regression tasks in fields such as social media, biochemistry, and energy. In social media, they are essential for sentiment analysis, financial analysis, and fraud detection. In biochemistry, MLPs model complex biological and chemical processes. In the energy sector, MLPs excel in load forecasting, energy consumption analysis, and machine optimization. Moving on to our approach in implementing fully fused MLPs on Intel GPUs, we will describe the inference and training algorithms. Specifically, we focus on the case where each layer's width, including input and output, is 64. The matrix operations during training and inference involve matrix multiplications and activation function applications. The training algorithm includes forward and backward passes for gradient computation, with considerations for activation functions and loss calculations. We optimize our implementation to maximize data reuse and performance, utilizing Intel's 1MKL for efficient matrix multiplications. Section Summary. In this section, we explore the application of multi-layer perceptrons, MLPs, in various fields such as image processing, video analysis, sentiment analysis, and robotics. MLPs are utilized for tasks like image classification, object detection, and model compression to reduce data size effectively. Additionally, MLPs are integrated into neural rendering, 3D reconstruction, and regression tasks in areas like biochemistry, social media, and energy forecasting. Section SYCL joint_matrix implementation of MLPs. In this section, we implemented the SYCL joint_matrix extension for MLPs. Our implementation is based on Intel's joint_matrix extension, allowing us to run code on Intel's XMX hardware for matrix multiplications. It's crucial to efficiently use the XMX hardware because the peak performance for floating point operations is very high. The Intel SYCL extension provides a joint_matrix object and functions to work with these objects. One important function we use is joint_matrix_mad, which performs matrix operations on the XMX hardware. For joint_matrix_mad to work, the matrices involved need to have specific sizes. Matrix A must be of size TM×TK, where TM can be chosen from 1 to 8, and TK depends on the device and data type. Matrix B must be TK×TN, and TN is device dependent. Matrix C and the output matrix of joint_matrix_mad must be TM×TN in size. It's important to note that joint_matrix_mad performs calculations in single precision for matrices A and B, while matrices C and the output are of type float. In our detailed description, we focus on the inference for the case where k equals n equals 64. We launch the kernel with specific work item and subgroup sizes to optimize performance. Each subgroup loads a unique block row from the input and stores it as joint_matrix objects. The weight matrices are loaded into shared memory, and computations are performed efficiently using joint_matrix functions. Our approach minimizes accesses to external memory by keeping data in registers and shared memory. We use local synchronizations to ensure smooth operations with shared memory. The training algorithm follows a similar structure to the inference but involves additional data storage for each layer. There are limitations to our approach, such as the need for a specific number of subgroups to fully occupy the device and restrictions on network width. These limitations can be addressed by adjusting batch sizes and network dimensions. Our algorithm optimizes performance by storing data efficiently and minimizing memory accesses. Section Summary. In this section, we implement MLPs using the SYCL joint_matrix extension, specifically tailored for Intel's XMX hardware. The joint_matrix object and joint_matrix_mad function are crucial components for efficient matrix multiplications on XMX hardware, with specific requirements on matrix sizes and data types. Our approach focuses on optimizing inference and training processes, utilizing SLM for weights and minimizing accesses to HBM or caches, while addressing limitations such as batch size restrictions and network width constraints on the Intel Data Center GPU Max 1550. Section: Roofline Analysis. In this section, we aim to minimize the number of accesses to the slower HBM memory. To evaluate our implementation's efficiency in achieving this goal, we compare it with the CUDA implementation using a roofline model with bandwidth constraints. We calculate and compare the arithmetic intensities of the algorithms for specific parameters. A higher arithmetic intensity suggests that more floating point operations can be performed per byte, indicating that performance is less constrained by memory bandwidth. However, a higher arithmetic intensity does not always mean higher throughput, as other factors like latency and frequency throttling can also affect performance. We do not consider the floating point operations of the activation function in our analysis. For our implementation, we use a certain number of work items and subgroups, where each subgroup computes a specific number of rows of the input. The number of loads of the weights matrix from HBM is inversely related to the number of subgroups in a workgroup. Each workgroup has its own shared memory, SLM, and needs to load the weights matrix from HBM into its SLM. We neglect the effects of the L2 cache in our analysis. Our algorithm achieves a high arithmetic intensity for the matrix-matrix product in hidden layers, indicating that each layer is compute-bound. Extending the analysis to the entire inference algorithm, including input data loads and output stores, we calculate arithmetic intensities for different numbers of layers. Our implementation shows higher arithmetic intensity compared to the CUDA implementation, leading to improved theoretical peak performance. The SLM accesses limit the performance of our SYCL code, but this is not a concern during training due to the lower limit imposed by HBM bandwidth. Comparing fused and non-fused MLP implementations, we find that fused implementations have significantly higher arithmetic intensities, improving theoretical peak performance. Our algorithm enhances the theoretical peak performance of the CUDA implementation on NVIDIA's H100 GPU. The performance achievable in practice is discussed in the following section. Section Summary. In this section, we aim to minimize accesses to slow HBM by comparing our implementation to CUDA using a roofline model with bandwidth limits. By analyzing arithmetic intensities for different algorithms, we show that higher arithmetic intensity allows more floating point operations per byte, indicating less limitation by memory bandwidth. Our algorithm achieves a high arithmetic intensity of 512 flops per byte loaded from HBM, demonstrating that HBM bandwidth is not a limiting factor and each layer is compute-bound. Section: Results. In this section, we demonstrate how our fully fused MLP implementation improves the performance of 4 common AI tasks: nonlinear function approximation, image compression, neural radiance fields, NeRFs, and solving differential equations with PINNs. We compared our SYCL implementation on an Intel Data Center GPU Max 1550 with the CUDA implementation on an NVIDIA H100 GPU and PyTorch using both Intel extension for PyTorch, IPEX, and CUDA backend. The comparison results are shown in a table. To ensure a fair comparison, we only measured the time for the relevant code parts where operator fusion is important, such as forward and backward calculations. The benchmark protocol was the same for both implementations, including the number of episodes, batch sizes, MLP architecture, ReLU activation functions, and linear output activation function. For nonlinear function approximation, we trained a neural network to approximate a given nonlinear function. We compared our SYCL implementation with the CUDA implementation for different batch sizes. We found that many methods in the fields of NERFs, neural compression, and pins use batch sizes between 2-16 and 2-22, where our fully fused implementation performs best. In our tests, we trained an MLP to approximate a nonlinear function f, r, 64, right arrow, r, 64. We compared the performance of our SYCL implementation on an Intel GPU with the CUDA implementation on an NVIDIA GPU. The results showed that our SYCL implementation outperformed CUDA, especially for smaller batch sizes. Our performance analysis revealed that the performance limitation was due to SLM memory latency rather than memory bandwidth. Ongoing investigations aim to reduce this latency. Overall, our SYCL implementation showed significant performance gains compared to CUDA, especially for training and inference tasks. Section Summary. In this section, we demonstrate how our fully fused MLP implementation enhances the performance of various AI tasks such as nonlinear function approximation, image compression, neural radiance fields, NERFs, and solving differential equations with PINNs. By comparing our SYCL implementation on an Intel Data Center GPU Max 1550 with CUDA implementations on NVIDIA H100 GPS and PyTorch, we show significant performance improvements, especially for batch sizes ranging between 2-16 and 2-22, where our fully fused implementation achieves optimal performance. Our tests reveal that the SYCL implementation outperforms CUDA, particularly in inference tasks, even when utilizing only half of the Intel device, indicating potential for further optimization to eliminate latency issues. Section: Image Compression. In this section, we explore different applications of neural networks in image compression, neural radiance fields, NERF, and physics-informed neural networks, PIN. For image compression, we train a multi-layer perceptron, MLP, called hat_f_theta to learn the color distribution of an image represented by a function f, r, 2, right arrow, r, 1. To handle high-frequency details that MLPs struggle to learn well, we use encodings G, R, 2, right arrow, R, n, to pre-process the pixel inputs. We employ a multi-resolution hash encoding G, R, 2, right arrow, R, 32, as input to the MLP. The training progresses over 1,000 iterations, with noticeable improvement in color accuracy and details as the training advances. The training time is 9.2 seconds for SYCL, 1.75 times faster than CUDA, and 4 times faster than PyTorch. The image can be reconstructed in 2.41 seconds using SYCL. Moving on to neural radiance fields, NERF. The goal is to learn a radiance field function f, r, 5, right arrow, r, 4. Similar to image compression, we use multi-resolution hash encoding to enhance the representation of high-frequency details. The training time for NERF is 1.93 seconds for training and 0.302 seconds for inference in our SYCL implementation, showing speed improvements over CUDA. In physics-informed neural networks, PIN, we apply our method to solve partial differential equations, PDEs, specifically the two-dimensional Navier-Stokes equation. By leveraging the PINNs framework, we train an MLP to represent the solution. The training time for PINNs is 0.55 seconds for SYCL and 0.60 seconds for CUDA, with significant performance gains compared to PyTorch. The evaluation of the PDE solution on collocation points shows an improvement of up to 8.95 times.